You may have heard of LIGO, the gigantic scientific device that's used to detect gravitational waves from merging black holes. LIGO uses what's called an interferometer to measure tiny changes in distance between the two legs of the detector, seen right here and right here. This is the interferometer used at LIGO. First, light comes out of a laser and is split along two paths. Then, it's reconverged on a detector, where it interferes with itself. When a gravitational wave passes, a different pattern will be produced by the interference on the detector. The purpose of this video is to explain what exactly an interferometer is and how it works. So this is a diagram of the interferometer that I'm going to build. So we have a laser over here, and it shoots light towards the half-silvered mirror that I'm going to take out of the coaster. So it acts as a beam splitter, so half the light will go straight through this mirror right here, and then half of the light will be reflected up towards the top mirror. And then, for both of these mirrors, they'll reflect their light back towards the beam splitter, and then half of the light will go to the laser, and half of the light will go through to the detector from both paths. Since the beams are overlapping on the detector, if there's a slight variation in the distance of the legs or the angle between the two beams, we'll be able to see an interference pattern on the detector from the overlapping waves. So this sine wave represents a light wave that would come out of our laser in the interferometer. And so I'm going to add another one, and with this knob I can change the phase difference between the two light waves. And so if there's no path difference in the two legs of the interferometer, then they would line up just like that. And so on the detector, what we would actually observe is the sum of the two light waves. So if they line up exactly, we just get constructive interference and the wave has twice the amplitude. But as we add a phase shift, eventually the summed wave disappears completely, and that happens when the two waves are totally out of phase. So when one is high, the other is low, and it cancels it out. And so as we add more and more phase difference, and we loop back around to them lining up, it'll constructively interfere again. And so that's how we'll see these fringe-like patterns where there are bright and dark stripes. Here I have a little interactive Mathematica applet that calculates the interference pattern that we observe from two beams that have no path difference. So the legs of the interferometer are the same, but the beams are slightly at an angle to each other. And so if we move these angle knobs, we can see that we can change the pattern that we see on the detector. So if I go to a higher angle, maybe not so high. Yeah, so if I go to a higher angle, we see that there are light spots and dark spots in between the two beams, one from each leg of the detector. And so this dark spot corresponds to an area where the waves are 180 degrees out of phase. So they're opposite from each other and they totally destructively interfere. And the bright spot right here is where the waves overlap, and they're in phase, and so they constructively interfere. This is a better rendering of what the beams look like when the angle is really small. We can see these fringes, and from this spacing of the fringes we can actually calculate the angle that the beams are separated by. And so at LIGO they do a very similar calculation where they look at the fringe and they determine the distance the legs have shifted. So I recently came into possession of these CCIT infinity mirror coasters because they changed their name and they were getting rid of them. But inside these infinity mirrors is a normal mirror, the LEDs, and then this special half-silvered mirror. So it lets half of the light go through and half of the light reflects. So you can see the phone that's filming this, and you can kind of see the infinity coaster through it right now. And so the half-silvered mirror and these normal mirrors are actually, and the laser, are actually all the ingredients that we need to make a really, really bad interferometer. So I have the interferometer kind of set up here. So we have the same as the diagram on the board. We have the laser going into the beam splitter, into the two mirrors, and then it's getting transmitted all the way over to that piece of paper. So right now it's not very aligned because those two dots should be on top of each other. So I'm going to do that and come back to you. Okay, so now as you can see, those two beams are pretty much as on top of each other as they're going to be with cardboard. In a real laser lab, the mounts would be much, much better than this, and it would be way better looking. So we should be seeing that kind of fringy interference pattern that I showed on the computer, or at least something that looks kind of like that. But we're not really seeing that. So what I'm going to do is use my glasses to make this image bigger. So before the lens in my glasses, the beams are perfectly parallel basically, and then the glasses make the beam diverge, so it'll get bigger as we get farther away. And so that makes the image over here a lot bigger. And we still, I can see it with my eye, but I don't know if the camera's going to be able to get it. Probably not. So I wasn't able to resolve the fringes with the video running, but I was able to get a kind of okay picture of it, so I'll put that here. So obviously I can't really show anything actually working with the really bad interferometer I made. So I'm going to borrow one from the Society of Physics students to actually show interference patterns that look like the ones I calculated, and try to demonstrate how Ligo would measure something like a gravitational wave. And I'll probably do that sometime this week and add it to the video before I present.